So, we are going to call that as incomplete similarity, incomplete dynamic similarity. So, let me set it up for you with an example. So, this is from a real life example, but I have changed the number and I am not disclosing to you the organization for which these experiments were done. So, consider an aircraft of length 10 meter and wingspan of 15 meter to fly So, actually the aircraft would usually fly at 30,000 feet or higher, but if it is a jet aircraft, if it is a piston propeller aircraft, it may fly at something like 5,000 feet if it is not pressurized, and if the cabin is pressurized, that it can go to a higher altitude. But to simplify things, I will keep it at sea level, and let us say at 100 meter per second. So, it is still quite fast. It is powered by 2 turbo propeller engines each propeller has a dia of 1 meter and RPM is 2000. So, I have just rounded them off to make calculations easy for us. So, tests are to be conducted in a wind tunnel of a 1/10 scaled model. So, find A, the test speed, B, the RPM of the propeller, and C, the ratio of drag of prototype to model. Okay. So, imagine that there is an aircraft that is being designed, okay, and these are the dimensions. 10 meter is the length, the wingspan is about 15 meter, and 100 meter per second, 2 engines, the diameter of the propeller is 1 meter each, and the RPM is 2000. And now we need to conduct a test of this inside a wind tunnel. Now, the wind tunnel test section may not be large enough to incorporate the full aircraft. So, it actually depends on what is the size of the wind tunnel. Okay. The bigger the size of the wind tunnel, larger can be your model, and if you have a larger model, it has 2 advantages. One is that, as you know, the Reynolds number is directly proportional to the length scale. So, if I have a larger model, I can actually model a larger Reynolds number, okay, effectively. The second more important thing is that when you scale down a model, then you will lose lot of geometric details. So, suppose my aircraft is going to take off and I have these wiper blades on the windshield of the aircraft, and when I reduce the model size by a factor of, let us say, 10 or 20 or 100 depending on the size of my tunnel, then I will lose all these geometric details, and therefore, the data that I get for the model testing may not relate to the prototype. Okay. So, therefore, the larger the model, the better off you are, but of course, as we discussed, the power required is usually cube of the speed, okay, and the size of the tunnel, if it is large, okay, you can imagine that a larger size tunnel would require huge power, and sometimes that power may not be available, not to mention the infrastructure costs. Okay. So, that said, let us go ahead with the analysis. So, let me draw for you the picture of the aircraft, and that would give us so let us say this is the tail plane. So, I am drawing a very, and this could be my wing. So, what is given to me is that there are two engines here, and they have a propeller, and the dia of each of these propellers is 1 meter and spins at 2000 rpm. The length, the wingspan, if I can call this as L span, that is 15 meter, and this length of the aircraft, so L fuselage, if I may call it, that is 10 meter, and this is the air coming at it. So, we will again make the same chart about model and prototype. So, the model is a 1/10 model, 1/10 scale model. So, we already know that if I am talking about the length of the fuselage, then the prototype is 10 meter. So, this would be 1 meter. If I talk about the L span, then this is 15 meter and this is 1.5 meter. Okay. If I look at the propeller, the length scale of the propeller, in this case the diameter, this is 1 meter and this is only 10 centimeters. Okay. So, it would be a very tiny propeller. And if I look at the speed, this is 100 meter per second and this I need to figure out. So, first let us argue what are the similarity parameters that are important for this problem. We are not interested in gravity related effect. Okay, so, Froude number is out. We are not related in pressure related effects directly, there is no imposed pressure, we are not interested in cavitation for the time being. So, Euler number is also not important. Okay. So, we are interested in Reynolds number because viscous effects are important, they lead to skin friction and therefore the drag. And because there is a propeller which is spinning, so we will have to account for the Strouhal number also. So, there are two numbers that are important here, the Strouhal number and the Reynolds number. If we want dynamic similarity, we must match the Strouhal number of the model to the Strouhal number of the prototype, and likewise Reynolds number for the model and prototype should match. Let us see what happens when we try to match them. So, RE model equal to RE prototype. What is RE model? Rho of air times the length. Now, it would become very important as to what is the length scale I choose. Okay. I could choose, for example, the length of the fuselage, which is 10 meter, or I could choose the length of the span, which is 15 meter, or I could choose the chord length of the wing, which could be much smaller than the fuselage or the wingspan, and so on and so forth. It turns out in the end it does not matter because all lengths are scaled. So, as long as I am consistent So, if I say that my Reynolds number is based on the length of the fuselage, and everybody talks about that length when they look at this analysis, there will be no confusion and everything is okay. But if I do not explicitly specify it when I define my Reynolds number, so I simply say my Reynolds number is 1 million, but I do not tell people it is based on which length and which speed, then I may base it on the fuselage, but some other person would base it on the wing span or the wing chord, and there would be confusion. So, it would be nice to explicitly say what is the length scale or which is the characteristic length that we are using. So, let us say we are going to use the fuselage as the characteristic length. So, therefore, this would be length of fuselage for the model times u for the model divided by mu, which is the air at sea level, and this has to be the same for the prototype. So, this is again rho air length of fuselage for the prototype, u for the prototype divided by mu air. So, I could cross out rho air, I could cross out mu air, and the Reynolds number matching actually would imply that my u for the model, the speed for the model, should be L fuselage for prototype divided by L fuselage for the model times the rho prototype, and because it is a 1/10 scale model, so this is 10 times up, and that would be 10 times 100 meter per second, and that is 1000 meter per second. So, I must do my test at a wind speed of 1000 meter per second. Okay. I do not know how many of you realize that this is a complete disaster. No modeling can be done at this speed for a variety of reasons. So, let me give you some. First, let us recall what is the speed of sound in air. As you will recollect from your high school physics, that was square root of gamma times the gas constant times the temperature. So, at sea level this is roughly 330 meter per second at sea level. Mach number is defined as u divided by a, and it relates to the compressibility effects. Okay, we have not done this explicitly, but it is good to remember that Mach number reflects the compressibility effects. Now, this I will call as m, Mach number. So, let us estimate what is the Mach number for the prototype. For the prototype, it is 100 divided by 330, okay, which is roughly 0.3. And in the aerospace community, it is felt that if your Mach number is less than about 0.3, then you can neglect the compressibility effects and treat the flow as incompressible. Okay. Let us see what would happen for the Mach number of the model. So, this would be 1000 divided by 330, which is roughly 3. This has become supersonic. So, actually now what we are doing is that although we were supposed to test the prototype at subsonic speeds, okay, at Mach number of 0.3, but because of our similarity rule and the choice of the length scales, we have entered into a regime which would become supersonic. And qualitatively, a supersonic flow would be very different than a subsonic flow. Okay. And therefore, this test will have no meaning. In fact, we should have, if the Mach number was important, then amongst the dynamic parameters, not just the Reynolds number and Strouhal number, we should have matched the Mach number as well. And you can see there is no way, if we match the Reynolds number, there is no way we can match the Mach number. So, there is a problem. Okay. And therefore, one has to use experience and some tricks to actually do the modeling. So, here is an example where we know what similitude tells us, what the similarity rules tell us, but we are unfortunately not able to use them and do the modeling. So, how do we tackle this problem? Let me say a few words about that. So, it is very clear that this speed is 1000 meter per second is undoable. Okay. A, it is unphysical because it would have Mach number effects and it would become compressible, and B, the tunnel that we have at IIT Kanpur, the National Wind Tunnel Facility, the maximum speed we can get in that tunnel because of the fan requirements and its design is 80 meter per second, 80. So, this is undoable. Okay. So, it turns out that if I used a 1/10 scale model, I am unable to match my Reynolds number, because the Reynolds number requires a speed of 1000 meter per second, which I cannot have. So, how do I model? Good, there is a way out. So, what we can do is we can try to see what happens to the drag coefficient with Reynolds number. Okay. As I said that we may be able to only go up to 80 meter per second in the tunnel that we have. So, for the model that we have, the 1/10 scale model, this is the limit of RE for the model. I can only operate in this regime, and this is because of the maximum speed that I have. Okay. The Reynolds number for the prototype, on the other hand, may be somewhere here. This is RE for the prototype. What people have seen from their experience is that usually the drag coefficient will reduce with increase in Reynolds number. So, you could, for example, get some curve like this. In fact, what people see is that beyond a certain RE, which we do not know what it is for in general, we will have to figure that out. CD does not change significantly with Reynolds number. Okay. So, it kind of flattens out. So, I could call this as CD infinity. That means this is the drag coefficient at infinite Reynolds number. What is possible is that we have a prototype that is very close to this regime. It is possible. Of course, we do not know, we do not have the data, but we can only operate in this Reynolds number range. So, possibly what we can do is we can conduct tests. So, I could do tests at these 3 Reynolds numbers. So, I could do a test at RE1, RE2, RE3, and then using the data here, I can reconstruct this curve and extrapolate. Okay. So, this is very smart. So, I have a model, a 1/10 scale model, and I could operate at Reynolds number less than this dashed line. Okay. So, I choose a certain Reynolds number, let us say 3 of them or maybe 4 of them, and I look at how does my CD vary as I change my RE. And then I am interested in the RE over here. so I can extrapolate. So therefore, what I could actually do is my algorithm could be the following, that conduct experiments at lower RE and extrapolate. Okay. So this is very creative. So here is a situation where because of certain parameters and your resource limitations, you are not able to do a dynamic similarity. Okay, you are not able to match the Reynolds number, and therefore you do this kind of a modeling. So this is also called as incomplete similarity. Okay. So let me repeat what we have done. We are not able to do experiments at the Reynolds number which is demanded by the prototype for dynamic similarity. We can only go up to Reynolds number, let us say up to here. So we track how does the drag coefficient vary with Reynolds number, and then use extrapolation to get the data over here. Okay. Great. So suppose I choose, so suppose now I decide to conduct experiments at 60 meter per second, 70 meter per second and 80 meter per second. Now I come to the next part of the question. So we were supposed to find out what is the test speed. So that we have concluded we will use 3 test speeds, okay, the maximum being 80 meter per second. Now I want to figure out what about the RPM of the propeller. Okay. The original prototype is operating at 2000 RPM. So this I will have to figure out through the Strouhal number. So let me now work with the Strouhal number. Let us now determine the rate of spinning of the propeller. So Strouhal number for the model should be the same as the Strouhal number for the prototype. As we did in the case of the pump in the last problem, we are going to write this in terms of the angular speed. So omega m times the length scale times the u of the model should be omega for the propeller in the prototype, L in the prototype and u in the prototype. This would ensure dynamic similarity if we match the Strouhal number and the Reynolds number. Of course, we have already sacrificed the Reynolds number. Let us see what happens to the Strouhal number. This would imply that omega for the model is actually u model by u prototype and L prototype divided by L model times the omega for the prototype. This here is 10 because I have a 1/10 scale model. So prototype is 10 times larger than the model. This I know is 2000 RPM. I know the u prototype, this is 100 meter per second. And now it turns out that depending on what is the speed of the wind tunnel at which I do the test, that will determine the omega for the model. So I can plug in these numbers, and what I will find is that omega model for um equal to 60 meter per second would turn out to be 12,000 RPM, and omega m for a test at 80 meter per second would turn out to be 16,000 RPM. So, imagine for the prototype my propeller was spinning at 2000 rpm, but now when I put this in a scaled manner inside the wind tunnel, I will have to spin it at this humongous rotation rate 12,000, 16,000 rpm, and it has to change with the speed of the test. Why is that happening? You can understand that physically from the fact that when the propeller is spinning, it has a certain tip speed. The tip speed is the angular speed times the radius omega r. So, that is the tip speed of the propeller, but my aircraft is moving forward with a certain linear speed. So, there is something called an advance ratio. How much does the propeller move, the aircraft move forward by the time this propeller goes through one cycle of rotation, okay? And that has to be maintained for dynamic similarity. So, that is why you would get omega that depends on the model speed. Alright, so therefore, what we are able to see is that for dynamic similarity you must match the Reynolds number which tells you the speed, but you are not able to, therefore, you do extrapolation, and for the Struan number matching you must do these RPMs. Okay, so, that finishes the second part. The third part is about the drag. So, that is a little bit easy to do because we know that drag is given as CD times half rho u square times L square. So, therefore, drag on the model or the prototype divided by drag on the model is simply CD is going to be same for both of them. So, I can simply write this as rho is going to be same u prototype squared L prototype square divided by u model square and L model square. And for 80 meter per second for equal to 80 meter per second, this ratio would turn out to be 156.25, which means the drag that acts on the model, if I had to scale it to what would happen for a prototype, that is the factor, little bit more than 150. Okay. So, then it involves designing the right kind of balances and so on. Okay, so, I hope you have got a fair idea of what is similitude and modeling about. Just to summarize the whole story in a couple of sentences, similitude involves the similarity. So, first we have to ensure geometric similarity, and then to get dynamic similarity we must match all the relevant pi's or the non-dimensional numbers, the independent ones. Okay. For example, if Reynolds number is important, it should be matched, Euler number should be matched, and the outcome would be that all the dependent quantities like the drag coefficients and so on, they will match. Okay. Then I presented you with an example where this matching is not possible, and we have to come up with our experience, with our creativity to still model the problem despite the matching not taking place. Okay. So, we will send you some practice problems, hope you take a go at them and understand this a little bit better. Thank you.